All right, so now we are ready for pushing it into example 4, where we're gonna formalize the steps here for finding vertical asymptotes, and as well as deciding among the vertical asymptotes which one can potentially be further a whole or not. Okay, so in the way how I see it, example 4 here truly is the advanced and the actual version of example 3 as we have done earlier. So we are first thing going to find vertical asymptotes, and then within those vertical asymptotes we're going to find out if any of those vertical asymptotes will even become the whole. Okay, so now let's write down the worded instruction of our example 4 here. Okay, so we want to find all vertical asymptotes, okay, and wholes. All right, of the given rational function. All right, so that's the worded instruction. So we're still finding vertical asymptotes. All right, and then on top of that, we want to even within the vertical asymptotes we have found, according to that logic I've been explaining. So within the vertical asymptotes we have found, we're going to even further decide, we're going to further determine if or whether any of those vertical asymptotes is going to become a whole. Okay, so we're going to find asymptotes, vertical asymptotes, and wholes here. Okay, so let's look at part A right here. So our function now, how about I'm going to name that O of x. And so with those problems I prepare in my quick notes right here, then it's how about x minus 2 all over, and then here we're looking at an x squared minus 4x plus 3. All right, so x squared minus 4x plus 3 is that polynomial in the denominator, and x minus 2 is a polynomial in the numerator. All right, so here we go. We have a rational function, and let's find, according to the goal of this problem, we want to find all VAs and wholes of this given rational function. Okay, so now just like that, this general conclusion now becomes a 2 steps guidelines right here. So the first thing is to identify all vertical asymptotes that tentatively can be. Okay, and those vertical asymptotes must happen at all the zeros in our denominator. Okay, so now that sets for us a guideline and a clear number of steps, and that's the intention of the whole example here. Is all about we want to formalize our work into finding a vertical asymptote and the wholes into the certain number of steps like that. Okay, so now we are going to find the zeros of our denominator. So as the first starting step for here, so you have seen that in example 3, at this point it is extremely beneficial to factor out completely your denominator, your polynomial in that denominator. So now in my next step, instead of rushing into directly finding the zero, I am going to spend some time finding the factor form of our denominator, because here it started out given here as a general form of our denominator. Okay, the general form of that polynomial. So now x minus 2 stays the same in the numerator, but the denominator here we can quickly factor that into, and we can easily factor that into x minus 1 times x minus 3. So the denominator, the polynomial in the denominator was now factored into 2 distinct linear factors. Okay, so now we realize that we will be having 2 distinct roots, 2 distinct zeros, okay, in that denominator. And so at this point we've been assumingly fluent with the skills of how to find zeros or how to find horizontal intercepts of a polynomial. So allow me to just quickly write from the factors. I am going to skip over the steps to find the zeros in the denominator. We just now directly see that first linear factor gave me a 0. So I'm going to list down the zeros. So as far as 0, we're looking at x equals 1. That's one of them. And the distinct factor corresponding to that is this factor right here, x minus 1, corresponding to this 0. And again, like I said, because allow me to assume, because I'm assuming that at this point anyone has already learned through anyone learning in this lesson here has already learned through my videos where I explained clearly about how to find zeros from a polynomial. So now I can skip that step because you've seen that and been fluent with that by this point. And so I can just simply skip that step and saying, hey, with this distinct linear factor, it is responsible for giving this 0. So I list down the zeros here instead of just showing the actual steps in finding those zeros now. All right, so now the other distinct factor here is going to give me another 0 separately. So x equals 3. So now I'm having 2 zeros of the denominator. So here, even though I'm using a short-term zeros, but really these are the zeros of the denominator. I apologize that my board space is limited. Okay, so now having these zeros of the denominator listed right here, the next step now is we are going to pretend, right, that any of these is a VA. So for now, let's pretend that any of these is a VA, or tentatively any of these is a VA. For now, any of these is a VA. So the next step, so really finding VAs, technically we're done right here. But the next step is to identify among these VAs, is there any one of these VAs will become a whole? Okay, and we have a clear criteria to test for that, to test for whether any of these VA will become a whole. And once it becomes a whole, it stays as a whole. So there's no such thing as being a whole and a VA at the same time. So that's also one thing I could have also mentioned in the earlier part prior to getting into this example. All right, so that's why it's making it now clearly as a certain step in the instruction. Once we've found all of our zeros in the denominator, any of these are now tentatively the VAs. And then just simply the next step, we're gonna identify throughout each one of these right here. We want to identify whether any of these can become a whole. And then so those remaining that did not become a whole stays as a VA. And then those that become a whole stay as a whole. All right. So in that way, one more time I'm swinging back to this board right here, and if the factor including its multiplicity, okay, if the factor including its multiplicity of the denominator that's corresponding to a 0, okay, at x equals a can be cancelled completely. This statement right here is the testing criteria for us. We're using that to test whether we are having a whole at one particular VA or not. Okay, or it's a way to decide whether our VA at that particular location x equals a can become or will become a whole or not. Okay, and again, remind yourself that once it becomes a whole, then it stays as a whole. It's no longer a VA. Okay, so now in this way, we're gonna test all of these zeros right here. The first 0 here is at x equals 1. Okay. The factor, the linear factor corresponding to that is here. And then with its multiplicity, this is the only factor, and then its multiplicity 1. Okay, so now is this distinct factor canceled out completely? Obviously it's not. Okay, this distinct factor, linear factor with its multiplicity being 1 right here, this factor was not canceled because there's no other factor x minus 1 in the numerator. So we did not cancel this. So without canceling this, this is now clearly a VA. So now I put a check there, okay, indicating that now we officially approve without seeing the graph. This is now a VA. And now we're done with that 0 at x equals 1 right here, and has concluded that it's a VA. And then in the next step, now let's look at the next 0 over here. It can be a VA or it can be a whole. So we're gonna test to see if it's a whole. If it fails being a whole, it's gonna stay as a VA. Okay. So now let's look at that one right here. So the factor responsible for this, the linear factor responsible for this 0 here is at x minus 3. With its multiplicity its multiplicity being 1 right here, right? This factor, this distinct linear factor did not get canceled. Okay, and so without being canceled here, then it stays at as a VA again. All right, so now I say, because earlier I was making a prediction that these are VAs, and now I approve that prediction because none of these became the holes. Yeah. All right, so now we have no holes. These zeros are all VAs. So now as we are concluding our answers here, VAs, as far as VAs, okay, we have them all. X equals 1 and x equals 3. These are all the VAs right here. Now we can put our answers in a box. Okay, and then as far as hole, the question is also asking for holes. Okay, and now we can just simply put in one conclusion, none. That's how we're finding it. So these are for now just at this stage right here, at this step right here, it's just we are checking. We list down all the zeros and we check. So because VAs are holes, only happens only happen at those places where we have the zeros in the denominator, and that was stated in statement number 1 of among our general conclusions. So again, step 1 and step 2. Now these are really more like a general guidelines of how we find VAs and further decide whether any VA can become, okay, a hole right there. That's how I see it. So starting out by default, any zero in the denominator will be a VA. But then further, can any VA there be a hole? And once it becomes a hole, it will no longer be a VA, it just be a hole there. So among these zeros of the denominator, there can be VAs or they can be holes. All right, so now I'm still going to leave this here for a little more while. Okay, let's get back on the other board and look at part B of our example. So I have to put in some instructions, some explanations of my steps, so that's why it took some time. But now once you are fluent and get the core idea of this, then when you're doing this work on your own, it's going to be a lot faster than how I'm doing it up here on the board, by the board, right here. All right, so this is now our empty graphing space here with decimals, the graphing utility. So now let me bring in our graph for part A of the example. So what we had there, all right, so this is our graph for the function r of x equals x minus 2 all over x minus 3 times x minus 1 in the denominator. All right, so the result here is clear with what we have found. We have two vertical asymptotes. One is at x equals 1. That's what we found earlier in part A. And this is 1 equals this is 1 at x equals 3 right here. Okay, and this is for the graph for our part A right here of the example. All right, so just now I actually put in the actual vertical asymptote to make it really clear and precise there. And this is now our graph, our vertical asymptote at x equals 3 for the graph of our function in part A of this current example. All right, so now let's look at part B of our example, where we are looking at another rational function. And allow me to name our function the same, r of x, but it's a different function in part B right here. All right, so r of x now is going to be, how about x squared minus 3x plus 2. All right, and then the denominator here has that polynomial x squared plus 3x minus 4. Okay, so it's a rational function, clearly. And then the numerator is a quadratic, the denominator is another quadratic. Okay, so very similar to the step I've done in part A, and just like that experience we have picked up from example 3 right there, we are in the next step we are gonna find the factor form of this denominator polynomial. Okay, so and really I'm gonna keep this numerator the same for now, and then here the denominator can easily be factored into x plus 4 times x minus 1. All right, that's how I factor my denominator polynomial into two distinct linear factors. So before we move into the next step, we can just quickly see, we can just easily see that each one of these distinct linear factors in the denominator is with multiplicity 1, because those are all we have. And so the factoring methods, yes, it's challenging. I brought it up in our discussion in our lecture about the polynomials, and you already sensed that it's not easy to get it done. But once you got it done, it tells you all about the zeros of your polynomial. So such a powerful technique. Just sadly, it's a little challenging to get it done. Okay. So now at that point, we are ready to list down all of our zeros. And again, allow me to skip that steps of how we find those zeros from your factor form of a polynomial. So here I'm just going to simply list down the zeros of the denominator. Okay. So how about allow me to be a little more specific than part A right here. I could have done this in part A as well. So here I'm saying zeros of a denominator. How's that? All right, the zero of the denominator. I want to be clear and specific about that. So now we have 1 at x equals -4. Simple. And then we have 1 at x equals 1. All right, and so now in this way over here, and when it gets to this problem, let's get really formal over here. I'm not going to even show that prediction. So like I said, these are just the zeros. And then at any of these zero, it can be a vertical asymptote, or it can be further a hole. And once it becomes a hole, then it won't be a vertical asymptote anymore. So right from or directly from any of these zero over here, let's just get straight into identifying whether it will become, or determining whether it will become a hole or not. If it won't become a hole, if it's not becoming a hole, then it stays as a VA, okay, by default. All right, so in that way, so once again, I repeat, I don't even have to write down that prediction step like I've done in part A, okay, because really at just these zeros right here, any of the zero can become a hole, and if it doesn't become a hole, it stays as a VA. It's simply just that. And so all we have to do is just go through each one of our zeros in the denominator and test to determine whether it will become a hole or not. Okay, and then we already had a clear guideline how to test whether it will become a hole at any of these zeros here. All right, so now x equals -4. X equals -4. In order to decide if the factor including its multiplicity of the denominator, of course now we're talking about in the denominator, so I shouldn't even have to have that. But if the factor including its multiplicity corresponding to a 0 at x equals a can be cancelled completely, okay? So now we're currently looking at x equals -4. So we want to find out at x equals 4, let's identify the factor corresponding to that 0 here is x plus 4. And now together with its multiplicity, will this be cancelled completely? X plus 4 with multiplicity 1, will that be cancelled completely? But now we are not able to answer that question at this point yet, because there's one missing link right here, easy link to find out. We need to also, so now we also realize the importance, how good it is that we also factor out the numerator. Okay, so every step in each of my example, I introduce a little extra steps, and at the end of a whole example, you're gonna put all of those together in a formal kind of work right here. So now we feel like we actually realize that we need to even further factor out the numerator so that we can possibly find out whether we can cancel this x plus 4 away. Okay, so now in my next step, the denominator has already been finished in factor form, so that has to stay the same in the next step. But the numerator now, I can factor that into x minus 2 times x minus 1. All right, and things starting to look very clear already. Okay, I don't want to say things too far ahead of time yet, but so now once again focus right at this particular factor responsible for this 0 in the denominator, including its multiplicity. Is this factor going to be cancelled? Ask yourself that question. And now the answer is no, it's not going to be cancelled. Okay, because there's no other common factor for that. All right, and even if maybe there's some other common factor of x plus 4 here, will it be completely cancelled? Meaning including all of it. including including with the multiplicity will be completely gone in the denominator, and that's not the case in this problem right here. All right, so now we affirm this here. Now I'm gonna indicate that. Now we're gonna have an indication clearly. This has to be a VA. It cannot be a whole right there. All right, so x plus 4 is a VA. Okay, and so now right here in this particular form where we completely factor numerator and denominator, let's move on to the next 0 in the denominator. The next 0 in our list of zeros of the denominator at x equals 1 right here. The factor responsible for that, or corresponding to that, is the x minus 1 factor in the denominator, and then its multiplicity currently is 1. Okay, we have x minus 1 as the factor corresponding to this 0, and again its multiplicity is 1. So now once again, in order to say VA or whole, we're gonna decide, hey, is this factor including its multiplicity gonna get canceled completely or not? Let's find out. X minus 1 to multiplicity 1, x minus 1 to multiplicity 1 in the numerator as well. So that means now we're going to cancel. For x minus 1 as a factor, we're actually going to cancel completely. We're going to cancel it away completely, including its multiplicity. And so now the resulting rational expression now is going to be x minus 2 over x plus 4. So think about it. Yes, after we cancel that, and again, of course, I mentioned this earlier. We can only cancel this because no matter whatever we're doing here, as long as we're working with this rational function, we are working with any x values except x equals negative 4 and except x equals 1, because though these are being excluded from our domain, they are the zeros of the denominator. And that's why as long as we're still staying away from x equals 1 and x equals negative 4, then x minus 1 is a non-zero quantity where we can legally cancel and turn that into this form. Okay? It's just a property that I constantly need to remind my students, because over time as we keep canceling our expression so easily, we will forget about that nature. Okay? So now canceling that out, we get to x minus 2 over x plus 4. So as far as the expression, and as long as we stay away from x equals negative 4 and x equals 1, we can reduce this math work, this expression, into simply just x minus 2 over x plus 4. And so now that factor x minus 1 is completely canceled. All right, that x minus 1 factor is completely canceled in the denominator. And so now we have a clear and solid conclusion. This is not a VA, this is going to be a whole. Okay? It's a whole like that. All right, so we have a whole at x equals 1 and a VA at x equals negative 4. All right, so now concluding our final answer right here. So as far as VAs, okay, we only have 1 at x equals negative 4. That's our answer. Okay, and as far as wholes, okay, we only have 1 at x equals 1. All right, and that's how we find vertical asymptotes and wholes of a given rational function. I'm not saying we're completely done with this problem. Okay, with this example, we're going to have more examples along the way, but now we've done about 2 problems already. Allow me to quickly swing over to my graphing utility at the computer station to show the graph of the two problems we've done up to this point, part B right here. And now in an empty graphing space, this is now the graph for our function of part B. All right, this is the graph for our function of part B right here. This came from x squared, our rational function x squared minus 3x plus 2 all over x squared plus 3x minus 4. Okay, and this is the function right there. All right, and so this function clearly, according to the results we have finished at the end right here, we have only one vertical asymptote at x equals negative 4. All right, so right at x equals negative 4, just like the result we have done in the problem on the board like that. And we had that. So here we're only using the graph here to confirm our result, but we already had our result guaranteed by the end of the problem on the board already. So this is, once again, the vertical asymptotes, and this is the only one according to the result we found like that. All right, and now for the other one, just like the result we have seen on the board, we are going to have really an empty hole. So the hole is here. All right, so the hole is here at x equals 1 like that. Okay, so this hole is the hole for our function r of x equals x squared minus 3x plus 2 and all over x squared plus 3x minus 4. All right. And so now let's look at another problem where we're going to really settle down our skills and get really clear with the steps, okay, of how to find VAs and holes for any rational function. And so I really put in a lot of explanations prior to getting to the examples here, because again, I always feel that need to prepare for anyone learning in this lesson in case you will plan to attend to take a formal calculus course where all of that details will be extremely beneficial. Okay, but otherwise, if you feel the earlier explanations of mine were a little too much, then feel free to fast forward the video there and just get straight into the steps here. It already had all the clear steps for you to find VAs and holes in any rational function. Okay, so part C of the example. Okay, so now I'm looking at x squared minus 4x plus 4. All right, and so now with our function currently displayed here, now this time our denominator is already in factor form. So x minus 3 times x minus 1 times x minus 2. So it saved some effort for us. Our denominator is already in factor form. It's a polynomial, okay, but it's already in factor form. And so it saved some efforts for us. So now with this rational function given to us here, let's find all VAs and holes of the given rational function. Okay, so now once again, the steps formally lay down as following. First, we're going to identify all zeros of the denominator. All right, and so our denominator is currently having that advantage of already in factor form. Okay, and so now we can easily list down, assuming that anyone at this point viewing this video lesson is already fluent with that skill of how you find zeros from the factor form of a polynomial. So now it's going to be x equals 3. That's one of the zero. We have an x equals 1, and we have an x equals 2. These are all the distinct zeros, okay, of our polynomial in the denominator of the function. So now once we have finished listing down all of the zeros in our denominator, and this is all they are. These are the distinct linear factors. So some other problem, there may be some multiplicities here, but in the end we only need to find our we find our zeros only from these distinct linear factors. Okay, and we can disregard about their multiplicity. Multiplicity back in our learning about the polynomials, multiplicity of zeros only affects the shape of the graph at that zero. Okay, so now in this case, let's look at the first one right here on our list. Let's identify the first one on our let's decide on the first zero on our list right here to see if it's going to be a whole or it will stay as a VA. Okay, so right here at that zero, we're going to decide if it's going to become a whole or not. And so the only way of doing that, we want to find out if this x minus 3, with its multiplicity currently 1 right now, this x minus 3, will it be completely cancelled? Will it be completely cancelled? So in that way, the only way to find out if it will be cancelled, we need to factor out the numerator. All right, so now in my further step, I need to put my numerator into factor form as well. So this goes into x minus 2 all squared. Okay, you can easily factor this out as x minus 2 times x minus 2, and that's in short x minus 2 all squared. Okay, and again, I feel confidence in the background of my students, whoever viewing this lesson right here, that you should be fluent with being able to factor this. Okay, so now we have the denominator x minus 3 times x minus 1 times x minus 2. All right, so one by one, as of this point, maybe you see something, you notice something about the some factor that can be canceled, but as of right now, at this moment, I'm looking at x equals 3, okay, as a 0 in our denominator. So the factor, the linear factor corresponding to that is x minus 3. And including its multiplicity, this x minus 3 is not cancelled, not cancelled. It's there. There's no other common factor with that in the numerator. And that means this one here, will it be a whole? Nope, it's not a whole. So that means by default it stays as a VA. That's how we can decide. Okay, and then at this point I don't think I need to keep swinging back and forth between this board and the board where I wrote down the instruction, the conclusions anymore. So now let's move on to x equals 1. So for this particular 0 over here, the factor in the denominator corresponding to that is the x minus 1. Okay, so this is the factor corresponding to x equals 1 over here as our 0. Now with its multiplicity, is x minus 1 with its multiplicity completely cancel, or can it be canceled completely? Nope, because the only factor we found in the numerator is the x minus 2. All right, so now this 0 at x equals 1 right here again stays as a VA right here. Okay, and so now we're done with that 0 at x equals 1, and see, naturally I already start picking up pace. Okay, and then x equals 2. Right at that 0 right here, the factor in our denominator corresponding to that 0 is the x minus 2. Now with its multiplicity in the denominator being 1, let's find out right here. See, the 1 in the denominator will get canceled completely into the 1 from the numerator, because the cancellation happens as following. Now x minus 2 with multiplicity 1 is canceled completely, and then in the numerator we have that cancel, but there's still 1 x minus 2 left over. That's the way how cancellation works, canceling out common factors. All right, so now in how I see it, in the denominator, that linear factor corresponding to x equals 2 together with its multiplicity is canceled completely. It's canceled completely to really become x minus 2 over x minus 3 times x minus 1. See, I'm documenting every single little step. So now in this simplified form right here, the x minus 2 factor in the denominator was completely canceled away. And that's what I meant in that general conclusion that I wrote on the other board earlier. And so now I have a firm conclusion here. This 0 at x equals 2 must be a whole. All right, must be a whole. That's how things happen like that. All right, so now we have a clear answer. We have some clear answers here for this particular rational function. As far as VAs, we have found, okay, see, sometimes VAs here is always optional plural like that, because sometimes it could be multiple VA, but sometimes there's only just one VA. All right, so as far as VAs, we found one at x equals 1 and one at x equals 3. All right, and that's the one. And as far as whole, and there could be possibly multiple as well. But here in this problem, we only found one at x equals 2. All right. That's how we found our answers for that. Okay, and so once again, I am going to swing over to my graphing utility at the computer station, okay, to show how the graph that's going to be displayed with decimals are being consistent with this. All right, so now with my empty graphing space right here in decimals, this is the graph for our function, okay, in part C that we just now finished. This is r of x equals x squared minus 4x plus 4 and all over that lengthy factor x minus 3 in product with x minus 1 in product with x minus 2. Okay, and so now just as the result we have already proven, we have a vertical asymptote at x equals 1. Just like that. We have another vertical asymptote at x equals 3 from the increasing order from the left to the right. But then at x equals 2, see, the graph is not able to show it, but we should be able, if we're doing a hand sketch on our own, we should be able to put the point there. But that point right at 2, comma 0 is supposed to be, or that point on the graph that's right at x equals 2 needs to be an open point right there, or a hole right there. All right, so this graph right here completes our understanding about the rational function in part C that we did in our example. All right, so now we are going to look at part D of the example. All right, so with this part D right here, our function. Now this time, thankfully, it's going to be given as following. X minus 1 in product with x plus 2 all squared. Factor form completely already. Okay, and now the denominator has x plus 3 in product with x minus 1 all squared times x plus 2. Another polynomial is given completely in factor form. All right, so this time, this is our rational expression where both numerator and denominator are given in factor form already. Okay, so which is a huge bonus for us because we wouldn't have to do that anymore. We would no longer have to do the factoring steps on any of these, because imagine with something like this, then the factoring work is going to be extremely challenging. Okay, so to save your time, a lot of times instructors, professors, and including me will provide the rational functions where numerator is either at least numerator or denominator already in factor form, so keeping things easy for your work, because generally mainly as a goal we just want to apply our skill into finding VAs and holes here. But I don't want anyone to get hung up, as at least for me personally, I don't want any of my students to get too hung up with just the process to factor out. Okay, because if that is too lengthy, you may forget about the main goal is to find VAs and holes and then eventually give up. Okay, and so now pretending that we already had our polynomials in the two parts right here, numerator and denominator are completely factored. And so let's list down the zeros of the denominator. All right. I should have written that in a way that it saves some space right here. All right, so then now as far as listing down the zeros in the denominator, this is what I have right here. I see some multiplicity among these linear factors in our denominator here. However, as far as the distinct linear factors, I only see 1, 2, and 3. Yes, this x minus 1 has multiplicity too. Okay, meaning there's an x minus 1 times x minus 1 twice. But in the end, as far as distinct, as I said, there are only 3 distinct linear factors here. Okay, so now immediately at this point, assuming you're already fluent with your skill how to find zeros from a factor form, then we have one right at x instead of writing z right here. X equals -3. That's one of our zeros in the denominator. We have another one at x equals -2, and we have one at x equals 1. 3 separate, 3 distinct zeros in our denominator. Okay, and so now once we've successfully listed down all of the zeros in the denominator, let's go ahead and identify whether each one of these will become a whole or not. And if it won't become a whole, it stays as a VA. The work is just simply like that. Okay, the work is all there is. And at this point, you may notice I have not done any cancellation yet because I want to show this is a thought process. We don't want to rushly cancel, and then in the end, we may even lose out some zeros right there in the denominator. And that's another logic right there. So right at start, even though the function is already given so easy for us, some people may mistakenly cancel away some factor out of habit. Believe me, in my teaching experience, I've seen students being quite confident with their factoring skill. And then at some point when we overuse our skill, for example, right here, we are able to factor and then cancel out immediately, two immediately canceling out the common factors. We're going to lose our goal that we need to see first all the zeros initially present in our denominator. And then from there, we use that cancellation to decide, as the next step, to decide any of these can be a whole or not. So if we immediately cancel these, there's a high likeliness that you will forget that there was initially 3 wholes, but you may only see it that as, initially there were 3 zeros, but you may only see that as 2 due to the reason that you forgot about the one you canceled away, if you did that first thing in line. Alright, so here, logically speaking, I'm holding on to the cancellation step from the beginning. I'm not doing that yet. I have to successfully list down all of my zeros before I cancel them away. The zeros in the denominator. And that's one of the intention. I brought up such an easy problem like this from the beginning for anyone to try. Okay, and so now with this x equals -3 as a 0, the factor corresponding to that is here. And now in this factor, we want to decide, is this 0, with that factor going to be a whole or not? Okay, and whole or not depends on whether this gets canceled completely or not. It doesn't. Okay, there's no other x plus 3 factor included in the numerator here. So x plus 3 in the denominator here, in other words, is not going to get canceled. It stays here in the next step. So in that way, now I have a clear decision. This x minus x equals -3 is now concluded as a vertical asymptote. Okay, it's a VA now. This is a VA. So clear. All right, crystal clear. Let's now move on to x plus 2. Okay, see, and like I said earlier, if we cancel the x plus 2 away right from the beginning in a rush, as soon as we came to this factoring form, there's a high likeliness that we didn't even have this listed on our zeros in the denominator list right here. That's dangerous. Okay, so I still have that here because I did not cancel it out, because I use that here and to decide whether we can cancel that out or not. Okay, and so now at this 0 x equals -2, at this 0 x equals -2 right here, we're going to decide, is it going to be a whole or it stays as a VA. So now if we're looking back at this, I see that I can cancel away the x plus 2. And the x plus 2 in the denominator here is with multiplicity 1, so I can cancel that completely away. And the numerator still is still going to have 1 remains in the numerator. But that does not change our decision, because at least the factor corresponding with that 0 is now completely canceled, including its multiplicity in the denominator. Of course, whole or VA, we're only talking about the behavior in the denominator. And so now in the denominator, that factor, including its multiplicity corresponding to this 0, has been canceled completely, or was canceled, or can be canceled completely. That's why I'm saying in my wording, notice in my wording I'm using that term can be canceled completely, because in my thought process I want to hold on to the cancellation step from the beginning. I don't want to get immediately into cancellation. That's why I didn't use a was canceled. Okay, but I'm saying we're still going to keep all of those, and we're going to use that as a decision line. Can we cancel this factor, or we cannot? Okay, and then can we cancel or not depends on if we still see another common factor from the numerator. And that's the idea. That's the reason why I worded it this way, instead of saying, if the corresponding factor was canceled completely. Because if we already canceled, there's a likeliness that we might skip out that that term right there, that particular 0. Okay. So now, once we have noticed clearly that now we can cancel away this x plus 2 right here. Okay. Of course, as far as the expression in our next step, we reduce down to, I don't think I need to use this bottom space right here. We bring it down to now just x plus 3 in parentheses times x minus 1 all square. Okay, and now I'm looking at x minus 1. X minus 1 times x plus 2. Okay, but at least that factor in the denominator is now canceled, because we said earlier we can cancel that when we still saw it. All right, so now this is a whole. This is a whole. Okay. This has to be a whole, and once we have decided that it's a whole, it won't be a VA. Okay, so either a whole or a VA only happens at zeros of our denominator. Okay. So now let's move on to the last one right here, and let's decide. See, once again, and see, I could have canceled completely all of my common factors. There's still common factors here. But I decided not to do that because we want to move on one by one throughout our zeros in the denominator. That's my thought process, and I hope you understand my intention when you're doing this. Okay? Otherwise, if we just boom, cancel immediately all of the x plus 2's away and all of the x minus 1 away, you're going to end up with such a too short answer, and then you may realize simply that, hey, x equals negative 3 is the only 0. That's the dangerous part right there in some other problem. Okay, and so now I'm still holding on to the x minus 1 without canceling it. So now I'm going to focus my attention to that. At this x equals 1 as a 0 over here, as a 0 of our denominator. The factor corresponding to that in the denominator, okay, with its multiplicity 2 right here, will this be canceled? Ask yourself that question. Can this be canceled completely? This factor with its multiplicity, can it be canceled completely if we would cancel that? All right, so now here's how I see it. As far as cancellation, if we really are going to cancel, the numerator get canceled completely away, but the denominator did not cancel completely. We only cancel 1x plus 1, and we still have a 1 extra x plus 1 factor left over. Okay, so now in my next step, that means my reduced or my simplified expression, my simplified rational function becomes the following: x plus 2 in the numerator, and then x plus 3 times x minus 1. So clearly the factor corresponding to this 0 in the denominator, including its multiplicity, did not or cannot be canceled completely. And now obviously it did not cancel completely. All right, so in that way, now I'm saying this thing is not going to be a whole. It's not going to be a whole. It failed that criteria to be a whole. So what is it then? It stays as a VA. All right, it stays as a VA. That's my logical arguments about tackling down these problems right here. So now at this point we have clear answers as far as VAs. Okay, and optionally, as far as VAs for this rational function, we're having two values, x equals negative 3, and another one at x equals 1. We have two answers. All right, and then as far as whole, okay, and in some other problem there may be multiple wholes right there. We have only one in this problem right here, x equals negative 2. That's how I document my steps and my thought process. Okay. All right, and so once again, before I'm leaving this example, let's quickly swing over to the computer station to show the graph from my graphing utility Desmos again. Okay. All right, so now on our empty graphing space here with Desmos, the graphing utility, this is the graph for our function. Okay, and the function itself was a little too lengthy to the point that I just don't want to say out the name right there. This is the rational function, the graph for the rational function right in our example 4D right there. All right, and so now apparently it already shows that we have two vertical asymptotes at x equals -3 and x equals 1 right here. So let me now put in the asymptotes in dotted black line like that so that we can make it real clear for the story. All right, and now at x equals -2, see, decimals or any graphing utility will fail showing it, but for us, the human being, we know how to show that. So if we would do a hand sketch version here, we have to put an empty hole here at x equals -2 on the graph. All right, so now that means right here I have that empty hole that I just now popped it in. All right, and that's the graph. That's the complete graph of our rational function that was in part D of our example 4 here. Okay, and that's everything here looks consistent as far as vertical asymptotes and hole. Everything looks consistent with our result on the board earlier. All right, and so now after having some thorough understanding about the vertical asymptotes of a rational function, allow me to put into your understanding this very good detail, but sadly skipped in many textbooks out there. But I feel this is a very good details understanding about the vertical asymptotes of any rational function. Okay, I don't plan to give any direct example on this detail. However, once you've learned it, this detail will live in a lot of the later examples throughout our discussions on the rational function. Okay, so now let's specifically focus on from what we've learned about the vertical asymptote. Let's dig in with some more the extra but extremely useful understanding right here. At least that's how I feel it. Okay, so now let me just come up with some function, some rational function. Okay, and then so the one I've had here is how about x plus 1 over, and here I have an x minus 1 times x minus 2 all squared. And for simplicity, I'm going to put this rational function, well, let's call it r of x. Okay, I'm going to put that rational function in, well, the denominator. I purposely put that in factor form. Okay, it's just simply for a reason that later on these two distinct linear factors in the denominator will make it easy for anyone viewing the video lesson to recognize that we will be having two vertical asymptotes here. Well, of course, at this point, we just got out of learning how to find vertical asymptotes of a rational expression. So there it is. So this function r of x, okay, r of x has, so now we know that we have two vertical asymptotes, two VAs at x minus 1 and x minus 2. And so at this point, we've been fluent and thorough with all of those details, how we can decide and really confirm that these are the vertical asymptotes. Okay, but now allow me to depart from the board here and get on my computer station. I want to really show the graph so that we can have a closer look at the behavior of the graph right at each of these distinct horizontal vertical asymptotes. Okay, so we want to specifically look at the graph behavior of this of any of these vertical asymptotes, so that we can add to our understanding some extra useful information, extremely useful actually. Okay, all right. So now on my empty graphing space, now allow me to use allow me to set up my graphing space here in an off-scale zoom right here. Okay, so that I can have a better complete view of my graph. So this is the graph of x plus 1 over x minus 1 in product with x minus 2 all squared. All right, so just as expected, we have a vertical asymptote here at x equals 1, just like that. And we have another vertical asymptote here at x equals 2. All right, but so my intention here is not to keep talking around or beating around the bush about, hey, we have a vertical asymptote here, we have a vertical asymptote there. We have already been fluent with that. This is what I want to get into right here. Now, so if we one more time, allow me to switch on my other board right there and still retain the picture here on the board. So if we're looking at that, or how about for now to organize our understanding this way, let's just look at each of these one by one. The first asymptote, okay, just focus particularly to this. You see, again, in our understanding, a vertical asymptote only happens wherever we have a 0 in the denominator. That's why it makes perfect sense that these two values, x equals 1 and x equals 2, these are zeros of the denominator. But then from our understanding about the polynomials, from our learning from the polynomials, any one of the zeros, well, if we're treating the denominator here simply as a polynomial, then any 0 here has a multiplicity. Okay, so now I'm going to bring the understanding. I want to show how the multiplicity of the zero, now I'm talking specifically about those zeros that give the vertical asymptotes. Okay, so now with the multiplicity being recognized here, how does that change the shape? How does that change the shape of our graph around the vertical asymptote? So now we know that there's a vertical asymptote here at x equals 1. But then this one here has a multiplicity 1. Or more generally, I see this as an odd multiplicity. Odd multiplicity at that VA right here. The VA, again, VA comes out, we have a VA because our denominator here as a polynomial has a 0 at x equals 1. And then more specifically, now we're going to get into seeing even further detail that the multiplicity, the multiplicity of this 0 in the denominator is a multiplicity 1, or more generally is an odd multiplicity. Look at what the graph is doing right at x equals 1 right there. Okay, so right now, in the way how I see that and drawing out as a conclusion from the graph right there, if we have a VA, at a 0 in the denominator and the multiplicity is odd, okay, so we have odd multiplicity, then at a VA x equals a, for example, okay, then this is what I see from that graph right here. This is the picture I see from that graph. At least right from the picture, when x equals 1 right here, when x equals 1, okay, the graph was doing this. From one side it's dropping, and the other side is going the opposite way. That's what happened in this graph. That's what happened in this graph right around that vertical asymptote at x equals 1. And so now, as far as the picture, the way I see is the two graphs, the two pieces on the graph around the vertical asymptotes comes to the vertical asymptote in the opposite direction. One side goes up, the other side goes down. One side goes up, the other side goes down. Okay? So, there are other cases out there. There are other cases out there that, yes, we have odd multiplicity. We have odd multiplicity, okay, at a given VA, at a VA, x equals a again. Some odd multiplicity, but the picture could be slightly different. We have a VA right here, okay, at x equals a, and then the picture now instead, but just like that, one side goes up and the other side goes down. So it could be left side is rising infinitely, and then the right side is pointing down infinitely. But in the end, as the two pieces of the graph on the two sides of the VA right here are getting closer to the vertical line itself, then the two pieces point in completely opposite direction. That's what happened to odd multiplicity at a specific given VA right there. And that's a generally some good details that about multiplicity, how multiplicity will affect the graph of our function. Okay, or affects the graph around a given multiplicity, the shape of the graph around a given multiplicity. So now in that case, same function. I am now going to change this same function just to enforce your understanding. So now we are currently focusing on this multiplicity here, on this VA here at multiplicity 1. So now I'm going to purposely change that to multiplicity 3 right here. I'm going to change that to multiplicity 3. Okay. And so now, but it's still odd. I purposely stay with the odd multiplicity right now. So we know that we will have a VA again at x equals 1, a vertical asymptote at x equals 1. But further we know now, we purposely looked at that VA when the 0 in the denominator here at x equals 1 has multiplicity 3. It's another odd multiplicity. Let's find out. Okay, to confirm what we've learned. So what we're expecting before we see the graph this time is one side goes up, the other side goes down, right around that VA at x equals 1. All right, so let's find out. All right, so back on the graphing space again with decimals. This is the graph. This is the graph for our function. That exact same function where I just simply change the multiplicity of this 0, the x equals 1, 0 in the denominator here to 3 right here. Okay, slightly modified from earlier. All right, so now let's look at the graph, which is right here, and now I'm going to swing by to the computer station and put in that vertical asymptotes. And so now currently we only need to focus to the vertical asymptote at x equals 1. So here it is. And once again we notice it's still having that similar shape as I was pointing out earlier. One side goes up, the other side goes down. The two sides, as the graph is getting close to it, the two sides are pointing in opposite direction vertically. I should have mentioned that earlier as well, but vertically, as we're getting closer to the graph, anytime our vertical asymptote has an odd multiplicity at that vertical asymptote, then as the two graphs, two sides of the two pieces of the graph on the two sides of the vertical asymptote getting close to, then one side points up, the other side points in the opposite direction. All right, so now in that way, we are able to put that into a generalization for now. Okay, and so now I'm going to put that into the first case. Let's write down a general understanding first. If, or let me write as the following. Okay. Let R of x be a rational function. Okay, let f of x be a rational function. In the form. All right, so allow me to write it in this way right here. So in the form sum numerator p of x divided by x minus a as a factor, because as long as x minus a as a factor in a polynomial, we've learned this from our understanding in the polynomial. So whatever numerator divided by the denominator, but in the form of a distinct x minus a to some multiplicity n, like that, multiplied with something else, q of x. These are all polynomial. All right. Let R of x be a rational function in a form thus. So just like what I've had earlier on the other board, see, x plus 1 over x minus 1 all cubed times x minus 2 all squared, for example. So this is my p of x. This is my capital P of x right here. Okay, and that's everything else in the denominator. That's the q of x, but then this is showing that x minus a to a multiplicity. All right, so because I want to specifically focus on the VA that happens right here at x equals a. All right, and so now this is the form that I want to primarily, pay attention to for now. And so in that way, if our rational function is in that form right there, okay. So anytime we're in that form, we know that the function will have a vertical asymptote. So needless to mention about that. So now I'm going to get straight into the point. The VA at x equals a has the following shape. The graph around the VA at x minus a has the following shape. All right. And so now I'm going to split that into two columns. Okay. So this is the x-axis, and from what we've learned earlier, the vertical line here, and I don't even need to worry about drawing the y-axis at x equals a right here. Okay. The graph is going to be either like this, all right, as we're getting close to the VA, two ends pointing in to the two ends pointing in the opposite direction. The right side points up, left side points down. Okay, and I'm talking about as we're getting closer and closer to the VA, that case, or this shape right here. Okay, vertical asymptotes. One side points up, the other side points down. Okay, the other side points down like that. Okay, so these two shapes right here, really it's just one same shape like that. But now that means for odd, okay, for odd n, or for n is odd. For n, the multiplicity here is odd. All right, so that's one case like that. All right, and so now we've investigated that through the graph right there, and this is the reason why now when I change to the third power, when I change this x minus 1 as a linear factor but raise to the multiplicity 3 right there, then the graph, once again, the graph right around the VA at x equals 1 has that shape. One side goes up, the other side points down like that, as both sides are getting close to that line x equals a. All right. So now let's have a look at that other vertical asymptote. So again, so we have another vertical asymptote. So now I'm going to pay all of my attention to this particular one right here. So let me erase these other extra information, and I can just go back to the multiplicity 1 here to keep things simple. Okay. So we were done talking about that. Let's leave it out. Let's now look at our entire rational function as something that just focus, that we pay our focus to that vertical asymptote at x equals 2. Okay. And now, let me put this drawing away. So now, yes, we know that this is at multiplicity 2, which is an even number. All right, and yes, this function here, along with the experience I have already brought up, then this function here, you can express that as some, see the whole x plus 1 in the numerator, we can call that some function, some polynomial in the numerator, divided by x minus 2 square times something else, times some other polynomial, but all of that is in the denominator. But what I see here is this is at this, so of course in this way we have a vertical asymptote at x equals a right here. But then in this case we're specifically looking into a multiplicity 2, or generally an even multiplicity. Okay, so now let's look at the graph again. Let's look at the graph of this original function, x plus 1 over x minus 1 times x minus 2 all square right there. Let's look at the graph here and look at this, but this time we're going to focus on this VA at x equals 2. We've learned from our technique, we've learned from our understanding that we already know and confirmed that this must be a VA. But let's look at the shape of the graph around that VA. All right. All right, so here in our empty graphing space here with decimals, this is the graph for the beginning function x plus 1 over the product of x minus 1 times x minus 2 all square right there. This is the one. And so as we have already been firmed that we have a vertical asymptote at x equals 2. So let's focus on this one this time. All right, and so now let's look at the shape of the graph of the two pieces of the graph around our vertical asymptote at x equals 2 right here. This time, as the graph is getting closer and closer to from the two sides of the vertical asymptotes, then the two sides of the graph, the two pieces of the graph, both pointing to in the same direction. Both sides of the vertical asymptote, as the graph is getting close to the vertical asymptotes, both sides of the vertical asymptote is pointing or is rising in the same direction, going in the same direction. See, so left side goes up and right side also goes up in this case right here. Okay? And now still retaining the picture of the graph here on that board. So now I recognize that for the case like this, where our rational function has a vertical asymptote as an x equals a with an even multiplicity, then it looks like the case for this particular problem, it went like this. Okay, x equals 2 is here. Okay, and then we have right side is pointing up, and the left side is also pointing up. I'm not worrying about scaling at all, but primarily it's the shape that, as the graph is getting close to both sides, is pointing in the same direction. Other case can happen, but one thing they should have in common. Other case, let's say even multiplicity at the vertical asymptotes. We may have the graph is doing the following. Both sides are pointing in the same direction, but both pointing down right here. This can also happen. All right, so that now brings us into another case where we're looking at the even multiplicity at a 0 in the denominator. Okay, and before I switch to my other board right there, I can also quickly raise this to a power 4, for example, to investigate, to make sure what we understand is correct, to make sure what we understand is correct, what we have explored is correct. So how about 4? Okay, so I can change this to 4. It's still even. Let's see if it's the same shape as following either one of the two right here. Both sides, the two pieces on the two sides of the vertical asymptote there is pointing in the same direction. Let's find out. All right, so now I'm changing this to power 4. So this is now the graph of our function. The graph for x plus 1 all over x minus 1 times x minus 2, but 2 to the 4th power. Okay, and so this is 2 to the 4th power. It's an even multiplicity for that particular 0. A VA happens at a 0 of the denominator, and once that VA appears to be in even multiplicity like this, this graph now doesn't look much different from the graph that we brought up earlier. Okay, the two sides again pointing up. The two sides, the two pieces of the graph on the two sides of our vertical asymptotes, both pointing up in this case right there. And then there could be other cases where they're both pointing down. But now, generally speaking, the two pieces of the graph around the vertical asymptote, they're pointing in the same direction. All right. And so now that is enough to make another generalization right here. Let R of x be a rational function in the form as written here. The graph around the vertical asymptote at x equals a has the following shape right here, but this time we switch into a different shape. We can go either, okay, we have a vertical asymptote here. The graph can be both pointing up like that, okay, at x equals a, or here's our graph, okay. The graph can be both pointing down, just like that, at x equals a again. All right, this is the case where for the multiplicity n is even. All right, that's what it is. So as I said earlier, before I begin introducing this particular detail, I did not and I won't have any particular example directly utilizing this skills. But be aware, this understanding, this detail will live in a lot of examples, problems, and also your assignment problems throughout the lecture here or throughout your assignments, especially when it comes to time where we put all of our detailed understandings regarding a rational function into the sketching or predicting the graph of a rational function, and that kind of skill will come. All right, and then that is where you're gonna see this particular detail, understanding the libs in any of those kind of problems there. All right.